Hi, everyone. Thank you for coming to our second webinar series hosted by the Institute for Augmented Medicine. Before we introduce our guests today, I'd like to share a quick overview of our institute. It's fairly new. So the Institute for Augmented Intelligence in Medicine was we launched in 2020, so not exactly the best year to launch things. So we are kicking it off. We feel like the first year is really our year to create a community for us all to share. And our mission is basically to be able to to bridge the computational methods with human expertise in order for us to advance medical science and improve human health. Out of that, our guiding principles are really focused around privacy and ethics and building community. The I.AIM is actually composed of 6 centers, and through these 6 centers, the Institute is pursuing specialized research, training, and outreach. I.AIM's leadership consists of medical and academic experts. With a true team effort, we are continuing to progress in pioneering the work of the latest technology to improve patient care. And for those of you who are interested in I.AIM and joining the team, please click on the membership link in the chat, which we will share. We're really excited to host also our first annual Big Ten Augmented Intelligence Bowl. Applications for that are due this Friday. Anybody who is in one of the Big Ten Academic Alliance schools is eligible to apply. So we're excited I'm going to turn it over to Firas Ahmad. Dr. Ahmad is an assistant professor at Feinberg School of Medicine. And he has been also a member of the Center for Health and Information Partnerships at the School of Medicine, and is part of one of our centers as well. And so without much ado, I'll hand it over to you.
Great, thank you, Nan, and thank you everyone for joining. I'm really excited to introduce Dr. Karandeep Singh and to hear his lecture today. Dr. Karandeep Singh is an assistant professor of learning health sciences, internal medicine, urology, and information at the University of Michigan. He's a nephrologist by clinical training and an informaticist. He directs the Machine Learning for Learning Health Systems Lab, which focuses on using machine learning and biomedical informatics methods to understand and improve health at scale. He also chairs the Michigan Medicine Clinical Intelligence Committee, which oversees the implementation of ML models across the University of Michigan health system. He's done a lot of really interesting work on the development, implementation, and evaluation of ML models embedded in routine care. And this includes an evaluation of the Epic Deterioration Index, which is a proprietary model that's been implemented in over 100 hospitals, including ours here, and used actively by many sites to support decision-making during the COVID-19 pandemic. He also has a great Twitter feed and does a lot of very interesting tutorials, including posting some of his thoughts on clinical decision-making, as well as software packages he's developed. And she occasionally has a really good dad joke in there. So I'm very much looking forward to hearing his thoughts on how to bring ML models to the bedside, and please join me in welcoming Dr. Singh.
Thanks, Faraz. Thanks, Nan, and thanks, Northwestern, for having me as a guest. I look forward to talking about how to bring machine learning models to the bedside at scale. And so I'll be using this as an opportunity to share from some of our experiences, going through basically all of the steps that we kind of think about after the model is developed. So developing the model, I think, is out of scope for today, but really talking about getting a model to the bedside, evaluating it at scale, and kind of getting that process going. So without further ado, I think let's get started. I already know that I think we're probably not going to make it through all of our slides through 1:45. So I'm going to be mindful of the time, and I'll probably flag some slides to skip over them. And if there are areas that we skip over that you want to come back to, or you have questions about, I'd love to kind of go back and spend time on some of those things as well. Feel free to put in questions into the Q&A during the talk. So Ravi asked, are the slides available? I'm happy for the slides to be shared. So feel free to make the slides available. And then, some of the questions I'll address during kind of the talk, others I'll kind of save to the end, just so we can make it through some of the content. Okay. So I think one of the first questions that always comes up is, why machine learning at all? There is not necessarily a good case for machine learning in all instances. And I would argue that machine learning really is just one small component of the learning health systems approach. So if you want to improve health at scale, you've got to basically identify a problem of interest. You've got to set up a learning cycle that includes formation of a learning community, having access to routine performance data that you can use to kind of learn from. Then this blue step on the top left corner is really taking that data and turning it into knowledge. And then finally, once you have information that can guide clinical care, you have to actually wrap some kind of an intervention around it. And that's that knowledge to performance step, so that that knowledge is not just kind of, people aren't just aware of it, it's actually being used to drive some kind of clinical decision-making process. So even though I think machine learning generally sits in that upper left corner of this diagram, there are aspects of machine learning that touch on the other colors as well. And most importantly, machine learning models can't make any difference in clinical decision-making unless they're linked to some kind of intervention to actually change practice. So in the context of ML, I would say the initial requirement you need to be able to integrate the model itself in the EHR, without having access to data from the actual model firing on actual patients. There's really no good that you can do as a result of machine learning, at least at scale. So this first step, although I said it's almost a prerequisite, is you have to have performance and turn it into data. I would say that in the context of ML really just refers to, you need the technical infrastructure to be able to actually run these models. Once you've got that, the main role that machine learning models play is in identifying high and low risk patients at scale. And the at scale part is important because, if you've got a patient with a rising heart rate and a dropping blood pressure, everyone knows that patient is sick and needs attention. And so that's kind of really important decision-making that you can make at the level of an individual patient. However, we have a rapid response team that rounds on sick patients every day, and they want to know at any given point who are, for example, the 20 sickest patients in the hospital right now who are currently not in the ICU. And for that kind of question, there's no easy individual way to answer it. You can look for who has a rising heart rate, who has a dropping blood pressure, but that's going to be a very noisy signal, and it's going to miss a lot of cases of people who are ill and have other indicators of being sick that aren't linked to those two, vital signs. So to be able to do those kinds of, risk stratification, you need access to, models that are running at scale on large populations within your health system. Ultimately, though, once you have access to that score, you have to do something with it. And I think broadly speaking, the main thing that we end up doing is allocating resources more effectively. What I mean by that is when we've got a score that identifies patients at high risk, we typically treat those higher risk patients more aggressively to try to prevent worse outcomes. And if we've got patients who are in a lower risk category, we often reserve our lower acuity care and try to prevent unnecessary testing on these lower risk patients. So an example of that I'll point to is that in April of 2020, when we were faced with the possibility of having a hospital overrun with COVID-19 patients, our hospital, along with many other hospitals around the country, were exploring whether we needed to open a field hospital to house our patients who were kind of less sick than others. And a question came up, which was, which patients are healthy enough that even though they need to be in the hospital, they can safely go to a field hospital and will likely not need access to ICU level care. So that's essentially a question of, can you identify low risk patients to move them to lower acuity care so that you can allocate resources more effectively on the high risk patients who need them more. So with kind of those things in mind, that's when people ask me, what is the role of machine learning more broadly? That's where I kind of see machine learning fitting in. You need the infrastructure to do it. You need to be able to accurately risk stratify high and low risk patients broadly. And then you have to be able to allocate resources more effectively for that risk stratification to actually make a difference in clinical care. So people often talk about early warning systems, and most of the examples today that I'll be talking about relate to early warning systems. When I say early warning systems, what I really mean are machine learning models that run on a fixed patient population. These may be models that run every few minutes, every day, or sometimes when an event occurs, like every visit. And in the case of sepsis deterioration and, for example, falls in the hospital, these are models that run every few minutes. And then when we're talking about someone missing a clinic appointment and trying to predict that and intervene on them, that's a model that doesn't need to run every few minutes. That's a model that can maybe run every day or every week or kind of on some lesser frequency. So the example I'm showing on the right is a deterioration index that we're running at our hospital. And you can see how this, it's scoring patients every 15 minutes. The x-axis is in hours, and that's why there's so many different points. You can see how if you're a clinician taking care of a patient, this score goes up and down. And so it's not necessarily any one given score that matters, but there might be kind of other patterns in here that are important. And the bottom two panels show patients who never needed ICU level care, never died, never needed mechanical ventilation. And the top two panels show two patients who ultimately got transferred to the ICU, one of whom depicted by the red line showing needed mechanical ventilation. So the challenges we'll talk about today is, first of all, is there infrastructure to implement models, and what infrastructure is there in place? Should we implement a model? Once we've implemented it, do we need to measure model performance? And if so, how do we go about doing it? Is a model good enough to use? So once we've got that model performance back, what do we do with that? Do we say approve, endorse, or not endorse? And then, once we've established the model is good enough to use, do the users actually agree on how to use the model? And then when implemented, is it actually effective? So when you're using it, does the model actually improve outcomes? And then finally, we'll talk about, what does governance look like in a health system for machine learning models? Now, I realize governance, I think, is probably a more relevant topic than some of the other ones, which, are kind of touch on different points. So if we're running short on time, I'll probably jump ahead and get into just some of the governance issues that have come up. So the question, the first place where we start is there infrastructure in place to implement ML? And, let me give you an example of when there's not infrastructure, what things look like. So this is the, scene at an academic medical center. A researcher comes along and says, we want to pilot our group's sepsis model. And if your IT group is very, open-minded and forgiving, they're going to say, great, let's build a web interface to your server. And, we're going to house your server behind our firewall. Predictions will never leave our health systems, kind of firewall, and this will be secure, and this is great, and this will work. And it likely will work. The next researcher will come around and say, well, we want to build or pilot this no-show prediction model. We want to predict which patients are not going to show up to clinic so we can use it to inform some kind of smart scheduling effort. And if your IT department is patient, open-minded, willing, they're going to say, great, let's build another web interface to your server too. And you can already imagine what's going to happen, and it's that a new EHR update is going to be installed. And suddenly, researcher number X comes back to you and says, why is my model no longer working? So what happened here? I view this as the non-infrastructural approach to trying to implement machine learning models. So if each of these researchers is like, is trying to get across a river, this IT department is handing them a bunch of canoes saying, here's your canoe, go ahead, go ahead. But when you have all these different canoes, all it takes is one failure for things to, stop working. And so, in this case, one researcher's variable got mismapped when the EHR got updated, and so things broke. And so the way to prevent this is to have an infrastructural solution. And so I think when I say infrastructural solution, I don't just mean an ability to run models in kind of one cloud environment. I really mean thinking about the whole model lifecycle. You need to be able to store models. You need to be able to have variables get mapped easily by the operations folks. You need to be able to manage model versions. So a model gets updated. How do you go from version 1 to version 2 non-disruptively while letting important stakeholders know that that's about to happen? There's lots of options on the technical side. Some are open source, some are vendor driven. And there's of course other cloud computing platforms like Amazon Web Services has AWS Lambda, Microsoft Azure, Google Cloud Platform. If you have a business associates agreement in place to share protected health information with them, the sky is the limit for what you can do here. But you need to pick one of these and understand how it's going to help you get models running in real time. So what do we have in place? We run a cloud-based machine learning infrastructure that's tightly integrated with the electronic health record. The infrastructure comes with a set of models that we can deploy. But probably most importantly for us, we can run any machine learning model in the cloud as long as it runs in Python. And that's a major benefit, I think, because you want model development to happen in a set of tools that are most familiar to the model developers. And you want a set of, you want tight integration with the EHR so that the operational people, the operational analysts doing, getting things integrated with the EHR can follow their usual workflow without having to learn some other language that they're not familiar with. So I think this gave us the best of both worlds. And so this is kind of what we're using right now. So you've got an infrastructure in place. That's essentially step one. Now the question becomes, for any given model or use case, should we implement a model in the first place? When I say implement, just to be clear, what I mean is simply integrating the model in the EHR and running it silently in real time. So I don't mean implementing a workflow. When I use the word use, like use the model, that's where I mean intervening on the model, based on its predictions to change something in the workflow. So implement a model is something that is very kind of passive, requires effort on the model developer side and on the operational analyst side. Use the model is where it's interfacing with clinicians to drive some kind of medical decision. Now, once you've identified a use case, whether that comes from a clinical lead or an operational lead or a researcher, you're usually presented with some kind of information about a model. And you have to decide, do we go ahead and approve it to even run silently in the EHR? And I'll just say, no matter what you do, this information has to be made based on imperfect information. If the model was developed at your own institution, then usually the model performance you're being told about is retrospectively calculated model performance. I mean, after all, the team wants to run it prospectively. If they already had prospective performance, they wouldn't be talking to you. If the model is coming from a vendor or coming from your EHR or a colleague of yours in another institution or in a peer-reviewed paper, then usually the performance that's reported is performance calculated at other institutions. And so that's great that it works at other institutions. That doesn't necessarily mean it works at your institution. And for vendor-driven models, one of the other caveats, and this is also true with researcher-developed models that haven't been published yet, is that any information they give you is usually going to have missing information. So when we report prediction models in the literature, we follow these tripod guidelines, which have like a series of best practices for what needs to be reported. I can tell you, having looked at half a dozen or a dozen model information sheets, that at least one of the elements of the tripod guidelines is going to be missing from each of those model information sheets. For example, it may not tell you where the model was trained, where it was evaluated. It may not tell you what a score of 50 means. Like, you might know that the model considers 50 to be high risk, but what does 50 actually mean? You might not know how the model handles missing values and so on. So the key takeaway here is it's important to have people with the right expertise to help make these decisions, because no matter, there's no mathematical way to purely, decide just based on some numbers that this model is good or not good enough to actually even just run it in the background. Because even running the model in the background requires work on the part of your operational analysts. So we'll come back to governance, as to who those people with the right expertise might be, those key stakeholders. But just recognize this step, you have to just do it based on imperfect information. Great. So you've got the model running, in your EHR, filing reports silently for each of its predictions. So every 15 minutes, it logs its prediction. And now you're able to go back and look at model performance to see how it's actually doing. So how do we actually do this? So real quick, I'll step back and ask, why should we even measure model performance? Like if we've got a model that has an area under the curve of 0.90 at 3 external institutions, do we need to know how it does at our institution? The researcher part of my mind says, no, external validation is great. It shows generalizability of the model. But I can say, having served in a role where I'm helping to oversee the implementation of models at our institution, what anyone in the room really cares about is, does the model work here? And while a model that's externally validated at a lot of places, that it has a favorable chance to work here, it's not a given. And so local validation can help uncover some of these issues. So this is just another scene at like one of our committees where we've met operationally to try to vet a model. We had a vendor come to us and say they've got a deterioration index model that has an area under the curve of 80%, which is pretty good, for deterioration index model. That's, I think, par for, similar to a lot of other, peer-reviewed models in the literature. And so they asked us, do you want to implement it? And we reviewed all the kind of model information sheets and said, we think it's good enough to run in the background to figure out how good this is here. So again, this is that imperfect information, had to make a decision because we don't know how it actually does here yet until we run it. 3 months later, we asked the model developer, the vendor, well, how is it doing here? So they did some calculations for us. And it turns out the area under the curve at our institution was 60%, which is pretty dramatically worse than what was reported at the other kind of peer institutions. And although we initially, finally did sort this out and figured out why this was happening, initially the answer from the vendor was like, we don't know why. And this just goes to show you that, you have to have a lot of faith that the numbers that are reported in any of these model information sheets are both generally accurate and accurate at your institution if you're going to partner with them. Because without access to, kind of independent validation of this stuff, you're essentially at the mercy of what your vendors can provide to you. And so partnering with your vendor, in some cases, doing the analysis yourself is really the best approach to try to, get around this. So like I said, local validation can uncover problems with the model. I won't get into these. This is one of the slides I'm going to kind of skip over, but there's a lot of reasons why a model that works at a lot of other places might not work at your institution, or even a model developed retrospectively at your institution might not work prospectively at your institution. Another common problem is model miscalibration, and I'm not going to go through the math here of how to fix miscalibration if it happens. I think it's described really nicely in this textbook. The main point is this even occurring? And without running a model locally and evaluating it in this way, you can't really even know if it's miscalibrated. So that's why, as kind of a general operating principle, we require models to be run for kind of 3 to 6 months in the background, depending on how broadly they're running and on how many patients, to make a determination of, is the model good enough here to actually link a workflow to and start to use. All right. So with that out of the way, how do we actually measure model performance? Let's say we've implemented a model to predict sepsis, and we have to figure out how good is this model. We often will start with defining a sepsis times 0. So we have to figure out, well, it's not just that they were built for sepsis. We have to figure out like when did the sepsis actually happen? And there's a whole variety of different criteria we could use to come to that times 0. Then, believe it or not, this sounds really simple, but we need to exclude predictions after time 0. Many of the vendor published evaluations of prediction models include all predictions from the encounter. And what ends up happening is that, a sepsis model looks really great if you're allowed to include the predictions that happened 10 hours after the sepsis episode when that patient developed septic shock and went to the ICU. The model looks not nearly as good when you bound it to only those predictions up to the time of actual sepsis, or maybe within like an hour after or 2 hours after, depending on what you think is the clinically relevant window. And then once you've done that, there's really 2 strategies to measure how well the model does. One is, how well does it do at the encounter level? So in other words, for each patient, take only their highest predicted value. and only count them once in the calculation. And then define the outcome as sepsis during the remainder of the hospital stay. That's kind of, if you use that and calculate model performance, that's your encounter level performance. Another strategy you can use is prediction level performance. So in this case, each prediction counts individually to the calculation. So if a patient has 1,000 predictions, you count each of those 1,000 predictions as separate predictions. And then usually when people report prediction level performance, they also use a prediction time horizon. So they'll say not just ever sepsis, but sepsis in the next X number of hours. So I'm going to skip the next two slides, but you can come back to them and take a look at them. But basically, when you use encounter level performance, you really penalize models that have a single bad prediction that's really high, because that is a patient who didn't experience the outcome but generated an alert. For example, that one on the bottom right, that hypothetical, if they had one bad prediction, that would mess up the area under the curve. And when we're talking about prediction level performance, your outcome window affects your area under the curve. So if you're predicting the outcome in the next 4 hours versus the next 10 hours, a high prediction 10 hours in advance is either a good thing or a bad thing based on what prediction horizon you think is important. So I typically use both of these strategies when I evaluate models because they measure relevant but different characteristics. But basically just know that when you see an area under the curve reported in a model information sheet, there's no such thing as a single area under the curve for a model. Usually you have to dig through the documentation to try to figure out what strategy did they use, and did they use either of these two strategies, or did they do something much more simplistic that included predictions, like for example, after the outcome already happened, which is not unusual to see in the literature. So the next question comes up is the model good enough to use? So I'm going to ask you guys to vote on this. So if you can go to chat, or actually, no, we got a vote coming up, and it looks like I get a vote too. So I'm going to go ahead and vote. So the question here is, well, I'm going to X out so you guys can't see this. So we have a model to predict sepsis. The model runs every 15 minutes on all hospitalized patients. Our encounter level area under the curve is 0.63. And so, 1 is the best area under the curve you can have. 0.5 is the worst area under the curve you can have. 0.63 is kind of a modest area under the curve. Our prediction level AUC is in the 0.7s with a 24-hour time horizon. And the model is well calibrated in this kind of 0 to 6% range, but very miscalibrated at predictions greater than 6%. So what I want you guys to vote on is this model good enough to use? Like if you were on the committee that had to decide to link a workflow to this model, do you think it's good enough? And then I can't see the actual results. So at some point, if we get enough results and you want to, if you or Faraz want to chime in to see how people are voting.
We are about to share them.
Cool. Okay. So
maybe
yeah.
not quite about. Do they come through, Meg?
Yeah, I see it in chat. So 27% voted yes, 73% voted no. And I'll be the first to tell you we are using this model right now. And so this is numbers that we got after the fact. These are not numbers that necessarily we're matching what we got from our vendor. But this is a model that's currently in use. Okay. This question though, as I posed it here, if our area under the curve was 1, I think everyone would agree we should implement this model. And if I said the model was well calibrated, everyone would agree, like that's a good thing. But the reality is simply that most models that we try to implement don't have perfect profiles on either their ability to rank order patients, which is what the AUC measures, or their ability to accurately classify risk, which is what the kind of calibration measures. And another way to actually answer this question is to ask clinicians, the following question: how many patients are you willing to evaluate to capture 1 case of sepsis? If you look at these early warning systems, the main cost of an early warning system, if you were to implement it, or the most direct cost, is time on behalf of either a nurse or a physician who has to do some kind of workflow in response to the actual model result or the model crossing a given threshold. Now, sure, there's a benefit to the patient as well if the model is good and the intervention is useful, but I'm just saying, under the assumption that the intervention is going to be kind of very modestly useful, the main cost of the model is really to the clinician who's going to have to do additional work in response to the model. So we can try to figure out how much work is a clinician willing to do based on the clinical context. And a decision curve can actually make this process mathematically computable, where you can say, given the amount of work a clinician is willing to do, does the model achieve a net benefit over a strategy that either results in you evaluating all patients or you evaluating no patients? So for example, if you're willing to evaluate 10 to 20 patients to capture one case of sepsis, you can think of that as equivalent to a cost-benefit ratio of a cost of 1 to a benefit of 9 for that willingness to evaluate 10 patients, or a cost of 1 to a benefit of 19 for that willingness to evaluate 20 patients. And you can plot the model's performance with respect to how that model performs with respect to what you're willing to tolerate for that clinical scenario. And the threshold that we have implemented at our institution is actually a threshold which corresponds to a willingness to evaluate 17 patients for each case. And at that threshold, we actually do have a benefit to using the model over trying to screen everyone, which is this gray line, or screening no one, which is the black line. So in this case, it turns out that even though the model seems like it has modest performance, implementing it is still a better strategy given the cost-benefit trade-off than simply evaluating all patients for sepsis or than evaluating no patients for sepsis. But it doesn't tell us whether implementing a model is actually better than the current clinical practice, although there is a way to plot that on this curve as well. So that's, I think, where this kind of thing can help to figure out if we were to implement it, is it even good enough to use? It makes that decision explicit as opposed to something more wishy-washy with just access to the area under the curves. Okay. So real quick, do users agree on how to use the model? For users to agree on how to use the model, they have to agree on the definition of the problem and the right course of action. And sepsis comes up repeatedly as such a problem. There's a ton of sepsis models in the literature that have been developed and that have been evaluated. And yet, when you think about what is the definition of sepsis, it quickly becomes apparent that there is not just one definition. There's a sepsis 3 definition, there's a CDC surveillance definition, there's billing criteria and billing codes, there's a Medicare SEP1 sepsis quality measure that has some of those characteristics overlapping with other characteristics or other scores built into it. And so the way you might define sepsis locally might depend on how you're being measured, on your ability to treat sepsis, or based on who you think truly has sepsis. And that's something that you have to ultimately come to terms with. So let's say we agree that this is what sepsis is. Do we agree on the right course of action? I really like this study by Downing and colleagues out of BMJ Quality Safety. And they didn't use a model. What they mainly did was deployed an alerting system that sent alerts in cases of severe sepsis, recommending that clinicians do a bunch of actions that are generally supported by guidelines. They looked at all kinds of process measures as outcomes. They looked at hard outcomes like mortality. And essentially, despite randomizing over 1,000 patients, they basically found no difference in any of their outcomes. And when they went to ask clinicians, like, hey, why didn't you give, why did most of you not give the requisite amount of IV fluids? Only 2 out of the 26 physicians administered the recommended amount of fluids. The physicians reported that they either were worried about that this wasn't the right thing to do for this particular patient, or they just disagreed with the guidelines, or they disagreed with the diagnosis of sepsis for that patient. And in fact, that disagreement with the diagnosis of sepsis was nearly 20% of the time. So it just goes to show you that, these are issues regarding workflow that you probably want to work out very early in the model request, way before the model is even evaluated. If you can't get, stakeholder agreement on what to do with the result of a model, it's not even worth taking that very first step, in my mind. So just a reminder, pages, although we've talked about, alerts and pages as a way to, operationalize models, it's not the only way. Pages or any other interruptive notification is obviously the most interruptive. They stop your workflow, even if you don't have the patient's chart open, you're just walking down the hall. This is alerting you that, you have to stop what you're doing and intervene. A little bit less, I think, interruptive than that is a clinical decision support alert, where it only fires if you have a patient's chart open or if you're looking at the electronic health record. So it's important enough to bring to your attention, but not important enough to interrupt your lunch over it. Another less interruptive way is just having a column in a clinician's sign out on, for example, the inpatient side that has a score that updates kind of in real time. We did that during the pandemic to try to figure out, which patients were declining. And each time you open a patient's sign out, you could rank order your list by, severity of illness based on a score. It's also useful to look at it almost like a vital sign whose trend can be visualized. When we have like a morbidity and mortality conference, and we're looking back and trying to identify why did this patient have a cardiopulmonary arrest. One of the things that our cardiopulmonary resuscitation team has started doing is looking at these deterioration indices that led up to the arrest to figure out, could we have identified this patient sooner through use of a series of scores running in the electronic health record. And then having access to a dashboard like our rapid response team utilizes to decide who to round on can be also really helpful for certain use cases. And then finally, patient counseling and shared decision making can also be aided by this kind of information. But one thing to realize is how you use the model has major implications on equity, as I'm sure you're aware. So I referred in a couple examples to a clinic no-show model. And if you use this model to, for example, double book patients, or to cancel visits kind of preemptively, or arrange for transportation, or switch visits to virtual, each of those potential interventions has some pros and cons with respect to ways in which it can help patients, or double booking can improve access if there are very few available appointments, but has major harms that if multiple patients show up, you may not be able to see all patients in a timely manner. So this is something just to think about, that what you do with the model has major implications on what effects it's going to have on your community. So is the model effective when used? So this is just a reminder that just having a model and using the model doesn't mean that using the model is actually doing anything. So this is just an example of a project I was involved in where we were developing a model to predict which patients were at high risk for utilizing the ER, and then using that risk score to identify patients for a randomized controlled trial where the highest 40 patients every month were being randomized to either an intervention group or a control group, and then seeing whether these patients identified by the model actually improved care when linked to an intervention. So the model was on this kind of top left corner of data to knowledge, and the intervention evaluation was in that knowledge to performance kind of upper right hand corner, where we were doing a randomized controlled trial to figure out whether the intervention actually works. So interestingly, this is not surprising to me, but we found that the model was good, but using it was actually ineffective. Mirroring, I think, some of the other work that's happened in this space of hotspotting or implementing workflows around models. So important to figure out. This is kind of the very, very last step, is trying to figure out, if it's not effective, do you need to de-implement it? Because if it's not working, what secondary benefit is coming out of it that makes it worth keeping around. So I think the rest of the talk really focuses on governance. Faraz, I'll get through these slides and then I'll turn it over to you if that's okay, because I think this is probably relevant to a lot of folks in this room.
Great.
So so at Michigan Medicine, in our health system, we have a sepsis model implemented. We have several other models implemented, but just as an example, we have a model that runs every 15 minutes. At a specific risk threshold, the model generates a page to a nurse. If a nurse does a secondary screen that's positive, a page goes to the physician. And so obviously there's like this huge, pretty intensive workflow built around this. And this was piloted for about a year on a set of 2 or 3 hospital units, and now is rolled out to the whole hospital. So involved a lot of work and coordination, and I would say most importantly, involved governance. So how did we get here? So like many other hospitals, we've for a long time had a clinical decision support committee that manages rule-based decision support alerts, what some people refer to as kind of best practice alerts in the electronic health record. That committee is around at most places because rule-based alerts are pretty transparent. It's a pretty routine way of implementing some kind of guideline recommendation into the ordering process to ensure that that guideline-based recommendation gets followed. So in July of 2018, we launched a new committee called the Clinical Intelligence Committee, which was in many ways a parallel committee to this decision support committee, but really formed to operationally oversee the implementation of machine learning models. In the space of machine learning at our institution more broadly, this is kind of how I see the platform, where we fit. So we've got groups focused on machine learning research that convene people from across campus, including the College of Engineering and the AI Lab. We've got a university-wide precision health initiative, which includes a implementation arm focused on getting some of these state-of-the-art models that were developed by researchers into the hands of clinicians by connecting them with important clinical stakeholders. And then once that's all been carried out, we have a clinical lead and in some instances, a research lead, in other instances, just a clinical lead with a model that's been identified, then it becomes an operations issue that comes to the Clinical Intelligence Committee. We are, like I said, we're a sister committee to the Decision Support Committee. And so, although we're not on the exact same line here, we're essentially parallel and have the same reporting structure through our governance. So we function like any other committee, within our IT environment within the health system. So who's on this committee? Our chief medical informatics officer is on the committee. Our chief nursing informatics officer is on the committee. Several associate CMIOs are there. And although pathologists are also physicians, pathologists have a unique understanding of the lab systems, and the lab systems drive a lot of these models based on lab results and when lab results are pended versus when they're finalized, et cetera. So we have pathology informatics represented. We also have analysts from our IT team. So folks who know how to actually do the technical build of these models in the EHR and where operational data lives. We have folks from quality analytics represented, so we can make sure that any decisions we make are closely tied to the kind of overall quality improvement efforts of the health system. And then we've got folks with learning health systems expertise. And we even have research informatics, because even though we're an operational group, we have researchers who want to be able to prospectively validate models. And to be able to prioritize these models, we need to have input from a research informatics lead. So for example, a model that is funded by the NIH will get higher priority potentially than a model that doesn't have any kind of funding because of the prioritization structure that we have. And then we obviously have ad hoc members which differ for each problem. So for sepsis, we interface closely with our hospital sepsis committee. And so either they would attend our meetings or we would present updates to their meetings. But broadly, we're essentially copying other, committees in our health system and fundamentally just helping to coordinate this machine learning in this space. All kinds of governance issues come up, and I won't go through these, but There's a lot of issues that come up surprisingly that we have to make decisions on. The final one is a model's performance dropping over time, which people don't even think about at the time that you're approving a model. So implementing and using the model is really only the beginning of the journey, and definitely not the end. Lots of evidence exists that after you've implemented a model, a lot of things can still go wrong. And so it requires kind of repeated attention by some kind of governing body. So I'll end with these thoughts that, implementing machine learning models within a health system is fraught with challenges that go well beyond anything that model developers think about. Governance and infrastructure are critical. And, the team that I presented to you is, I would say, an unusually multidisciplinary team for an IT team. And so be prepared to kind of establish this kind of unusual team that may not necessarily exist in other parts of your health system. And the other key is, I think, to make ML implementation the norm and not the exception. So don't set up, different processes from what all the other committees are doing. Learn from what the other committees are doing, like the decision support committee, and follow established processes so that this becomes something routine for the institution and not the exception. So with that, thank you for your time and attention, and looking forward to conversation and questions.
Thank you so much. That was an outstanding talk. You covered a ton of material, but in a very incredibly clear and concise way. So thank you again for joining us today. So we do have a few questions that I encourage other people to put in their questions as well. I'm going to start with one from Josh Chima, who's actually one of our STAR Cardiology Fellows and soon to be AI Fellow in the Bloom Cardiovascular Institute. And he says also, great talk. But then he has a question about bias, which you touched on in your talk. So he writes, one of the things he worries about in deploying an ML model is the risk of perpetuating bias. Considering an algorithm that will help recommend patients for certain interventions, what are things researchers can do to try and not further pre-existing bias and referral patterns for said intervention? And this is related to a project we're actually working on right now in our health system.
That's a great question. And I would say the question touches on really two aspects, one of which is the things that a model developer needs to do, and one of which is what the model implementer needs to do. And so what I won't talk about, but there's a lot of research around, is what a model developer needs to do. Because usually in the shoes that, when I'm wearing my operational hat or turban, I essentially am thinking about the model is the model. I don't have any control over the model, and the question really is it perpetuating bias? So one of the things we did with the Epic Deterioration Index when we were evaluating it in our Annals of American Thoracic Society paper, we looked at differential performance. So does the model perform differently in different subgroups, like different racial groups, folks with different comorbidities that were vulnerable in the setting of COVID-19? Another thing you can do is to see, does the model give you higher average predictions or lower average predictions for specific subgroups? That's just, I think, scratching the surface of things that you can do. It's not a definitive thing, because even if you identify situations where the model has higher predictions for a subgroup, those predictions might be appropriate if a subgroup has a higher risk to begin with, because more of them experience the outcome due to other underlying factors. That can be an appropriate thing. And I think you're familiar with this, but I'll point everyone to Ziad Obermeyer's fantastic paper in Science, where he highlights how even if you exclude race from models, doesn't mean that your models don't discriminate based on race, because of other things that correlate with kind of structural inequities in our system. So it's not a simple issue, not a simple one-size-fits-all solution, but awareness, I think, at least can help with some of that evaluation, and also highlights why you need an interdisciplinary team that is not simply all clinicians or all kind of informatics people.
Great, thank you. That's really helpful for our current work here. Another question is from Dan Schneider, who's part of our who's the manager for research analytics team in our EDW. And his question is, have you done work on any ML projects to identify potential patients for clinical trial recruitment initiatives?
So the one example, so that's a great question. The one example I shared was actually exactly that. We had access, it was a quality improvement project funded through the Center for Medicare Medicaid Innovation, CMMI. And we actually had access to, from 3 different health systems, all EHR data for everyone living in 2 counties in Michigan. We were running models in the, to evaluate people at high risk, people who may or may not have had care yet at one of our institutions. And then we were cold calling high risk patients to enroll them in an RCT. So patients would get a call out of the blue that said, you're a high risk patient based on your risk of going to the ER. We want to, connect you with a care manager, social worker to try to, see if we can help in any way. Would you like to participate in a trial? We haven't done it more broadly for other things, but I think, there is a path to do that. The challenge, I think, becomes, you have to be careful because you are now running your model on people who haven't consented to identify patients for a trial. So it's not that different than I think using specific criteria, but you need to have a darn good model that you can trust, because if your model's not good, your trial might fail because of the model's inability to identify the right population. So it's doable. I think I've seen discussions about it. Ours was one example. Another example was the very prominent New England Journal paper on, I think, predictive hotspotting from the Camden, New Jersey care management initiative.
Great. There are a few questions about infrastructure. And there's one question from Ravi about, have you explored the use of model as a service, as a delivery mechanism to help circumvent the need for acquiring infrastructure and the integration of EHR using APIs? So maybe you could use that to talk a little bit more about the infrastructure you have at Michigan, how long it took you to stand that up, and some of the strengths and limitations of that approach.
Yeah, so, the models as a service sounds, I think, on the surface of it, very attractive. I view this as like AWS Lambda is a way that you can run arbitrary models in the cloud. And let's say those models are running behind your firewall, or you've got some kind of business associates agreement with Amazon that lets you run models in the cloud securely. Then, everything seems fine. The problem is this: you need to not only have the model logic running in the cloud somewhere, you need to connect the variables in your model to variables in your daily real-time electronic record feed. And you ideally want your analyst on the operations side to use standard processes that they already know. So this is the main thing that led us to adopt the Epic cognitive computing platform at Michigan Medicine. I know a lot of institutions that are peer institutions have adopted this in some way, shape, or form. For us, the main reason to do this was that the models can run in Python if you purchase the kind of cloud version of that, which means that the model developers can develop models in the tools that they know best, but the operational analysts connect all their stuff using Reporting Workbench, which is something they're very familiar with. So it was the least amount of learning for both stakeholders to do it. Now, that said, getting our first cloud model up and running easily took us, I think, 6 months. So even once the infrastructure was stood up, there's just a huge learning curve. Someone mentioned one of my R packages in the chat. Well, I'll just say, essentially the process is like wrapping your model into a Python package where you're chasing a bunch of breadcrumbs from various different virtual trainings about what file needs to go where, what metadata needs to go where. And that just takes time to learn. And I think it's still kind of in its early stages. So even though it's functional, there are still kind of bugs that are some of our research groups actually identified in the process of getting our first model live. Now, that said, our second and third model took, I think, 2 weeks, 3 weeks. The actual work was maybe like as low as 4 to 6 hours from our analyst. So that really was where the benefit is worth it. If it's only a couple hours work for our analyst, it could be like 100 hours of work for a researcher. It's our analyst time that operationally constrains what we can actually do. If it requires a week of analyst time, doesn't matter if it's easy for the researcher, that model is a no-go. So that was, I think, the main win for us was it requires little analyst time once we figure out the kind of workflow. And we've got several different research groups now running several models, some in the background, some that are now being linked to clinical workflows.
And one of the potential strengths of ML models is the ability to use integrate longitudinal data and time series, or leverage unstructured data sources, whether they be notes, images, things like telemetry. Has any of your work tried to leverage these deeper unstructured data sources as part of a model?
So on the operations side, no. On the research side, yes. And I think some of that gets into the limitations of the existing technological infrastructure that we selected. We can't access notes in our selected infrastructure. Now we have a place where we've had notes indexed, pre-processed, and through the work of David Hanauer, who's one of my colleagues, and a fellow of AMIA, he's done a tremendous work in natural language processing at our institution, but that right now is separated from what we can do in our infrastructural platform. So right now we don't have operationalized models in that space that are using natural language processing. We're working on our first getting our first imaging model off the ground, but it's not I think a learning experience for us, just like it is for everyone.
Great. We're almost out of time, but I do want to ask one last quick question. I do see a lot of our trainees here on this call with medical students, residents, fellows. So for someone who wants to develop a skill set that you have and sort of be at the leading edge of implementing these models, what advice do you have them at that stage of their training?
Yeah, so I think one thing I didn't know about until I was actually a nephrology fellow was the existence of the entire specialty or field of biomedical informatics, and more specifically clinical informatics. And there is actually there are master's programs in it, there are fellowship programs in clinical informatics, and there's actually a national board exam you can take in clinical informatics. And increasingly, if you want to find your way into a role where you are like an associate chief medical informatics officer, which I am not, but a lot of the ACMIOs we have, I think, have similar interests as me. But if you want to be on that path, I think pursuing a master's program in biomedical informatics or pursuing one of these postdoctoral fellowships that lead to that are linked to a clinical training fellowship, I think is a fantastic idea. Because a lot of these things are soft skills. Now you'll have to decide what you want to be an expert in. So you're not going to be an expert in machine learning coming out of a program like that, but that will give you, I think, the building blocks to then extend your skill set to be able to, focus on the niche that you find most relevant.
Great. Well, I just wanted, on behalf of the Institute, and everyone here, I want to thank you again for that outstanding talk. And we will be hosting this lecture as well as sharing the slides. And please, everyone on this call, please feel free to join the Institute, our mailing list, if you want more information about future events. And please follow Dr. Singh on Twitter too, because you'll learn a lot, as I have. Thank you again, and thanks everyone for joining.
Thanks, everyone.